We are now going to find Coulomb's law when two charges are placed in a medium and then find out what happens if it is placed in different other mediums. So let us consider we have two charges Q1 and Q2 placed in vacuum, or you can even consider placed in air. Both mean one and the same. So the force between these two charges, which is placed in air, in free space or in vacuum, is given by the expression F naught is equal to 1 upon 4 pi epsilon naught modulus of Q1 Q2, that is the product of the two charges, upon square of the distance between the two charges. Now let us assume that the medium between the two charges is being replaced by water. So I have considered the same two charges with the same distance of separation inside another medium, that is water, or you can even consider it is placed in glass. What should be the expression that we get when these two charges are placed in another medium apart from air or vacuum? In that case, the force between the two charges, which is placed in a medium, should give you an expression which is 1 upon 4 pi epsilon modulus of Q1 Q2 upon square of the distance between the two charges, where epsilon represents permittivity of the medium. Further, this epsilon is going to give us a new concept, or you can even call it as a new factor known as relative permittivity, where relative permittivity is also known as dielectric constant. So it is telling us about the insulating property of the medium in which the charges are placed. So to define relative permittivity or dielectric constant of a medium, we say it is the ratio of the medium to the permittivity of free space. So relative permittivity can also be expressed as epsilon upon epsilon naught, where epsilon is permittivity of the given medium and epsilon naught is permittivity of free space. Let us assume Q1 and Q2 now placed or separated by a distance r, and both of them are placed in vacuum. So the expression that I can get from this is given as 1 upon 4 pi epsilon naught Q1 Q2 by r squared. Let us call this as equation 1. Similarly, let us consider the same two charges now placed in a medium with the same distance of separation. The expression that I should now get is 1 upon 4 pi epsilon Q1 Q2 upon r squared. Let us call this as equation 2. And now if you divide equation 1 by equation 2, I should be getting force in air or vacuum divided by the force in the medium should give you the right hand sides divided with respect to each other, where I get the following equation. And if you simplify it further, you can get rid of all the terms that can be cancelled. As you can see, I can cancel 4 pi in both the expressions as well as Q1 Q2 and r squared. You are only now left with 1 upon epsilon naught divided by 1 upon epsilon, which further gives you an expression which is written as epsilon upon epsilon naught. Hence you get an expression for force in vacuum divided by force in medium given as epsilon upon epsilon naught. This epsilon upon epsilon naught should give you relative permittivity, which is known as epsilon r. Hence the dielectric constant or relative permittivity of a medium is defined as the ratio of the force between the two charges separated by a distance in air to the force between the same two charges separated by the same distance in a given medium. The point to note over here is force in air or vacuum, that is the permittivity of air or vacuum, is 1. That is relative permittivity of air or vacuum is considered to be equal to 1. Whereas for any other media, relative permittivity is always greater than 1. It can never be less than 1. We now define definition of 1 coulomb, or this can be also asked as the definition of SI unit of charge, where we know coulomb represents SI unit of charge. Let us consider those two charges Q1 and Q2 separated by some distance and again placed in air or in vacuum. Please remember this word that has been used, that both of them are separated in air or vacuum, is most important to be used over here. Further, I can write this expression as force in vacuum can be given as 1 upon 4 pi epsilon naught Q1 Q2 upon R squared. We have taken the modulus of the charges so that we are only concerned with the magnitude of the two charges. Now, if Q1 and Q2 both of them have similar charge on them, we can call them as identical charges, where we have considered the charge on each one of them is equal to 1 coulomb, and let us say the distance of separation between the two charges is also 1 meter. So from here I would get an expression for force in vacuum given as 1 upon 4 pi epsilon naught 1 coulomb into 1 coulomb upon 1 square, which ends up giving me an expression force in vacuum is equal to 1 upon 4 pi epsilon naught, where we know the value of 1 upon 4 pi epsilon naught is 9 10 to the power of 9 Newton. Hence you can now say that 1 coulomb is that charge which, when placed at a distance of 1 meter from another charge of same magnitude in air or vacuum, experiences a repulsive force equal to 9 10 to the power of 9 Newton. Hence, the charge on each body should be equal to 1 coulomb.